All right, today we are going to unpack a statistical puzzle that, honestly, it sounds more like a riddle, but it's actually fundamental to how we make sense of the world through data. We're talking about the paradox of the picked elephant.
So let's just jump right in with a question that, on the surface, sounds completely impossible. Imagine this. You've got to figure out the total weight of a 50 elephant herd, but you can only weigh one of them. How in the world could you possibly do that?
Well, the answer isn't just a formula. It's actually a story, a bit of a cautionary tale, you could say. It's all about logic, probability, and yeah, a statistician who got himself fired from the circus for being, well, a little too clever for his own good.
Okay, so here's the scenario. This comes from a classic thought experiment by a statistician named Debabrata Basu. You've got a circus owner. She's got 50 elephants, and she needs a quick estimate of their total weight. Like right now. Now, her plan seems totally logical, right? She picks an elephant named Sambo, who she knows is pretty much middle of the road in terms of size. She weighs him, multiplies that number by 50, and boom. Simple, fast, probably a decent ballpark guess. But here's the statistical problem. It's not random. The other 49 elephants had literally zero chance of being picked. So, in walks the circus statistician, and he is absolutely horrified by this lack of proper procedure. He says, no, we have to make this unbiased and statistically sound. But his plan to make things fair, well, it gets a little weird.
Okay, so check this out. The statistician sets up a random draw, but he rigs it. He gives Sambo, the owner's original choice, a whopping 99% chance of being picked. Then he takes that leftover 1% and splits it evenly among all the other 49 elephants. So, technically, every elephant could be chosen.
And this is where the whole thing just goes completely off the rails. The owner says, okay, so what happens when we pick Sambo, which we will 99% of the time? The statistician shows her the formula, and it gives a perfectly reasonable estimate. But then she asks the killer question. What if, by some 1 in a million chance, we pick Jumbo, our biggest elephant? And the formula? Oh boy. To account for Jumbo's tiny probability, it multiplies his weight by an enormous factor, leading to an estimate for the herd that is just astronomically ridiculously huge. It makes absolutely no sense.
And that, of course, is the punchline of the whole story. The circus owner, seeing a method that has even a tiny chance of producing such a bonkers result, fires the statistician right there on the spot. So, what was this guy even trying to do? Was he crazy? No, he wasn't crazy. He was just using a very powerful, very legitimate statistical tool called the Horvitz-Thompson estimator. Now, his application of it was terrible, but the idea behind it is actually the foundation of how we conduct surveys all over the world. So here's the big idea. The Horvitz-Thompson estimator creates an unbiased estimate by giving more weight to the things that are less likely to be picked. You basically take the value of whatever you sampled and divide it by its probability. The thinking goes like this. If you happen to pick something that was super rare, it must be representing a whole bunch of other rare things you didn't see. So you got to boost its importance in the final calculation. And this is what that looks like in math terms. Don't let it scare you. That big E-looking thing, sigma, it just means add it all up. So for every item I in your sample, you take its value, which is t, you divide it by its probability, pi, and then you just sum all those results together. That's it. That's your total estimate. Okay. The whole elephant story is fun, but it is super extreme. So let's look at how this works in a much more realistic situation. Let's say we need to estimate the total sales for a group of 4 supermarkets, but we only have the budget to survey 2 of them. Here's our setup. We've got 4 stores, and you can see they're all different sizes. Now, we've designed our survey so the bigger stores, especially Store D, have a much higher chance of being included in our sample. And that makes sense, right? Its massive sales numbers are going to have a huge impact on the overall total.
Let's walk through it. Let's say our random draw picks stores C and D. Okay, we grab their sales figures, 24,000 and 245,000. We look up their inclusion probabilities from the table, and then we do that Horvitz-Thompson magic, divide each store's sales by its probability, and then add those 2 new weighted numbers together.
And there it is. Based on a sample of just 2 stores, our estimate for the total sales of all 4 is about $317,000. That's pretty cool. And just so you know, the actual total sales for all 4 stores was $300,000, so that's a really solid estimate. But, getting the number is only half the story. Just as important is knowing how confident we can be in that number. Is our estimate likely to be super close to the real thing, or could it be way off? We have to measure the uncertainty. And that brings us back to the elephant in the room, literally. The real statistical crime in the circus story wasn't that the estimator was biased. On average, over thousands of tries, it would have been right. The problem was variance. The possible answers were all over the map, from reasonable to absolutely insane. That makes any single estimate completely useless. So, statisticians have formulas to measure this wobble, this variance. They let us calculate something called the standard error. Just think of it as a margin of error. It's a single number that tells you how precise your estimate is likely to be. If we go back to our supermarket example, we can calculate that standard error. A smaller number is always better. It means our estimate is more stable and reliable. This shows us that our guess of 317,000 isn't just a shot in the dark. It has a measurable and pretty decent level of precision. So I hope you can see this isn't just some quirky academic exercise. This whole idea of sampling with unequal probabilities, it's a bedrock principle of modern data collection. It's how the real world is sampled. Seriously, it is used everywhere. When the government puts out unemployment figures or GDP numbers, this is the kind of math behind it. When public health officials track a disease, they use these methods. Even political phone polls use a version of this. The whole key is just to design your probabilities thoughtfully, unlike our poor friend at the circus. So what's the big takeaway here? It's this. Weighting by the inverse of probability is an incredibly elegant way to ensure fairness. It makes sure that every single member of a population, whether it's a huge elephant or a tiny one, a giant corporation or a small mom-and-pop shop, gets represented properly in the final picture.
It's really a beautiful solution to a tricky problem. So the next time you see some big national statistic, maybe you'll think about that circus owner, her 50 elephants, and the wonderfully clever math that helps us make sense of it all. Thanks for tuning in.